Discharge through an external cylindrical mouthpiece. We have definition of the mouthpiece. A mouthpiece is a short length of the pipe which is 2 or 3 times its diameter in length. If this pipe is fitted externally to the orifice, the mouthpiece is called external cylindrical mouthpiece. It's increase the discharge through an orifice. This is the cross section of the external cylindrical mouthpiece. The jet of liquid entering the mouthpiece contract to form a vena contracta at section CC. This section CC you can see in the figure. This is the figure. Let H height of liquid about the center of mouthpiece. This H is height of liquid about the center of mouthpiece. VC velocity of liquid. AC area of flow at vena contracta. V1 velocity of liquid at outlet. A1 area of mouthpiece at outlet. CC coefficient of contraction. This H you can see in the figure, height of liquid about the center of mouthpiece. VC velocity of liquid at CC section. AC the area of flow. V1 velocity of liquid at outlet. A1 area of mouthpiece as at outlet. CC coefficient of contraction you can see in the figure, and we want to prove this derivation for external cylindrical mouthpiece. What's the derivation? The first of all, apply continuity equation. Continuity equation is equal to A1 V1 is equal to A2 V2. This is the general formula for continuity equation. If we want to apply continuity equation at CC section and 1 you can see in the figure, this we want to apply continuity equation at CC section and 1 it shows and in the figure. AC times VC is equal to A1 times V1. We want to find, I'm going to find VC. VC is equal to A1 V1 by AC. We can write also V1 by AC by A1. AC in it means actually by theoretical area is equal to coefficient of contraction. Coefficient of contraction is exact value is 0.62. We can substitute here instead of AC by A1. VC is equal to V1 by 0.62. From this is the equation of VC, your velocity of the liquid at CC section. From section CC, the jet of liquid suddenly enlarges at section 1. The loss of air due to sudden enlargement is given by this HL is equal to VC minus V1 whole squared by 2G. VC, we have value of VC V1 by 0.62. We can substitute here instead of VC V1 by 0.62 minus V1 whole square by 2G. We can take common V1 from V1 square by 2G. It's the remaining part is 1 by 0.62 minus 1 whole square. HL is equal to 0.375 V1 square by 2G. This is the value of HL. And also for find out the last derivation we can apply from Bernoulli equation to point A and 1 we can get this is the Bernoulli equation PA by rho G plus VA square by 2G plus ZA is equal to P1 by rho G plus V1 square by 2G plus Z1 plus HL. We have value of HL. HL is equal to 0.375 V1 square by 2G. ZA and Z1 is both are is equal. V1 is negligible and VA is negligible. It means VA is equal to 0. And P1 by rho G, its atmospheric pressure 8 is equal to 0. PA by rho G is equal to 0. Z1 and Z2 both are equal and they are cancelled out. And VA is negligible is 0. It's H plus 0 is equal to 0 plus V1 square by 2G plus HL. We have value of HL 0.375 V1 square by 2G. HL is equal to we can take a common V1 square by 2G. We can after that we will get this value 1.375 V1 square by 2G. This is the last V1 is equal to 2GH, and we are going to find the V1, and after that we are finding the V1 is equal to root 2GH by 1.375. After the last value of V1 is equal to 0.855 into times root 2GH. We have theoretical. Now we have theoretical velocity of liquid at outlet. Theoretical velocity of at outlet is equal to root 2GH. And coefficient, what's the coefficient of velocity for mouthpiece? Coefficient of velocity is equal to actual velocity by theoretical velocity. We have actual velocity 0.855 root 2GH, and theoretical velocity we have root 2GH. We can substitute this value here. CV is equal to, instead of actual velocity, you can substitute 0.855 root 2GH, and instead of theoretical velocity you can substitute root 2GH. Root 2GH by root 2GH is cancelled out. The remaining parts CV is equal to 0.855. This is the contraction coefficient of velocity for mouthpiece 0.855. For mouthpiece, since the area of sheet of liquid lead outlet is equal to the area of mouthpiece at outlet, CC is equal to 1, means coefficient of contraction is equal to 1, and we are going to find coefficient of discharge. Coefficient of discharge is equal to CC into CV. Coefficient of contraction times coefficient of velocity. We have coefficient of both, or we have value of both, or coefficient of velocity and coefficient of contraction. Coefficient of contraction is equal to 1. Coefficient of velocity is equal to 0.855 and is equal to the last value of CD is equal to 0.55. This is the derivation and the value of coefficient of velocity and discharge and contraction. This is the derivation of for external cylindrical mouthpiece. Thank you.